Good day viewers, we shall talk on elementary theory of functions. We begin with types of relation in economics. For that, we shall have to first try to understand ordered pairs and Cartesian product of sets. Let us begin with order pairs. We have noted that the order of elements is not important in a set, but when we want order to be important, we write round bracket A B instead of curly bracket A B, which is the notation for set. We call it an order pair. We emphasize that A B is not equal to B A unless A equal to B. Also, A B equal to C D if and only if A equal to C and B equal to D. And note well that A B is not equal to C D if and only if either A is not equal to C or B is not equal to D. As for example, to record weight of each student of a class of 30 students, one can form order pairs. Roll number of student and his weight in specified units. Thus, 150 would mean that student having roll number 1 has weight 50 units and 2560 would mean that student having roll number 25 has weight 60 units. Clearly here 20 and 25 and 25-20 are different and have here totally different meanings. Cartesian product. If two sets x and y are given their Cartesian product, which is denoted by x cross y, is defined as x cross y equal to the set of order pairs A B, A is in x and B is in y. Example, if x is equal to 1, 2, 3 and y is equal to A B C, then x cross y will be 1A, 1B, 1C, 2A, 2B, 2C, 3A, 3B, 3C. Y cross x will be A1, A2, A3, B1, B2, B3, C1, C2, C3. It is clear that x cross y is not equal to y cross x. As we know that points on a line can be associated with real numbers, similarly, points on the plane can be associated with elements of R cross R. Rectangular coordinate plane. A plane with two orthogonal lines meeting at a point O, which will be referred to as the origin, is called the rectangular coordinate plane. If necessary, after rotating the plane, we visualize this plane as shown in the figure. The horizontal line through origin is most often named as x axis and the vertical line through O is named as the y axis. Further, the right half x axis is called the positive x axis and the left half x axis is called the negative x axis. Similarly, upper half of y axis is called the positive y axis and the lower half y axis is called the negative y axis. There is a one-to-one correspondence between the set of order pairs of real numbers, that is R square, and the set of points of a plane when we consider the plane as a Cartesian coordinate plane. Suppose order pair of real numbers A B that is, when an element of R square is given, we associate with this order pair a point P in the Cartesian coordinate plane by fixing real number A on the x axis and then fixing the real number B on the y axis. Thus, P is at the intersection of two lines which are parallel to coordinate axis, that is, x axis and y axis as shown in the figure. In other words, we associate the point P, which is obtained by moving distance A along the x axis and then moving distance B along the y axis. Also, the other way, when a point P is given in the Cartesian coordinate plane, we can associate with P an ordered pair of real numbers C D, that is, an element of R 2 by drawing two lines through P which are parallel to coordinate axis and then associating with the intersection points the real numbers C and D on the x axis and y axis respectively as shown in the figure. Thus, we can establish one-to-one correspondence with the set of all ordered pairs of real numbers and the set of points on a plane which is called Cartesian coordinate plane. The Cartesian coordinate plane is divided into four quadrants. The first quadrant consists of order pairs AB, where both the coordinates A and B are positive. The second quadrant consists of order pairs AB, where the first coordinate A is negative and the second coordinate B is positive. The third quadrant consists of order pairs AB, where both the coordinates A and B are negative, and the fourth quadrant consists of order pairs AB, where the first coordinate A is positive and the second coordinate B is negative. Now, we move on to a relation. A relation R is a subset of x cross y. Any such subset establishes a relation between a certain point y of set y and certain points x of the set x. As for example, 1. If x is equal to 1, 2, 3 and y is equal to ABC, then R is equal to the set of order pairs 1A and 2B is a relation. 2. Suppose X is the set of all persons who were alive in world on 1st January 2000 and Y the set of all women who were alive in this world on 1st January 2000. Then S is equal to the set of order pairs xy in x cross y such that y is a mother of x is a relation. 3. The set S equal to the set of order pairs xy in R cross R such that y is equal to 1/2 into x is a relation. 4. The set S is equal to the set of order pairs xy in R2 such that y is less than or equal to x square is also a relation. And 5. The set S equal to xy in R2 such that x square plus y square equal to 1 is a relation. Now, I will make some remarks on this. 1. Suppose a relation R that is a subset R of x cross y is given. Note that it is not necessary that for every element x in X, there is some y in Y such that order pair x y is in our relation R. In our examples, example number 1, 2 and 5 are such examples. In example 1, no element of the set Y is related to 3. In example number 2, if X, a person who was alive on 1st January 2000, but whose mother had died and was not there on that day, then for such X in X there is no Y in Y such that x y is in R. In example 5, it is very clear that if we take x greater than 1 or less than minus 1, then for such x there is no real number y such that x square plus y square equal to 1, and therefore, there is no y such that x y is in R. 2. Relation R may be such that for some x there are more than one related y values. In this case, the relation R is called one many. In our examples, example number 4 and 5 are such examples. In example 4, there are infinitely many values of y which are related to x equal to 1. Here 1 1, 1 0, 1 minus 1, 1 minus 2 and so on are in R. Function. When a relation R, that is a subset of x cross y, is such that for each x in X there is uniquely related y, we say that this relation defines a function. In this case, we write y is equal to f x whenever x y is in R. Often a function is visualized as, here x is equal to the set ABC, y is equal to the set 1 2 3, and R is equal to the set consisting of order pairs A1, B1 and C2. Remarks. 1. Functions are also called mapping or transformations. 2. Given a relation R, different x may have same related values, that is x1 y and x2 y may be in R, as for example, S equal to the set of order pairs x y in R2 such that y is equal to absolute value of x. Here 1 1 and minus 1 1 are in S. Similarly, 2 2 and minus 2 2 are also in S. 3. We should also note that every function is a relation, but a relation need not be a function. The earlier considered set S equal to the set of order pairs x y in R2 such that x square plus y square equal to 1 is a relation, but this relation is not a function. This relation fails to be a function for two reasons. Number 1, with x equal to 2, there is no related value y. 2. With x equal to 0, there are more values related. Here 0 1 and 0 minus 1 are in S. 4. Function is also specified by the notation f colon x to y, where for each x in X a unique value f x is specified, and clearly then the set of order pairs x comma f x such that x is in X is a subset of x cross y is a function in the strict sense of the definition. Conversely, if relation R as a subset of x cross y is given, that is also a function, then f from x to y is defined by writing f x equal to y if x y is in R. When a function f from R to R is given, graph of f is nothing but a function looked upon as a relation, the set of order pairs x comma f x such that x is in R, which is a subset of R square. Types of functions. Constant function. Functions of the type y equal to f x equal to 10 are called constant functions. They do not change their values. Whatever may be x, y equal to f x is constantly equal to 10 here. The graph of such a function is a horizontal line. Polynomial function. The function of the type y equal to f x, which is equal to a 0 plus a 1 x plus a 2 x square, so on up to a n x raised to n, is called the polynomial function. Note that here a 0, a 1 up to a n are fixed real numbers, that is, they are real constants. Depending on the different values of n, the functions that we get are given definite names. These names are summarized in the table. We have different values of n and the corresponding formula and then the name. For n equal to 0, we have y equal to f x equal to a 0, which is called constant function. For n equal to 1, we have y is equal to f x, which is equal to a 0 plus a 1 x, which is called a linear function. When n equal to 2, we have y equal to f x equal to a 0 plus a 1 x plus a 2 x square, which is known as quadratic function. When n equal to 3, y equal to f x equal to a 0 plus a 1 x plus a 2 x square plus a 3 x cube is called a cubic function. Rational functions. A function of the type y equal to 1 plus x square divided by 1 plus x square plus x cube, wherein y is given as a ratio of two polynomial functions, is called the rational function, and if nothing is mentioned, it is supposed to be defined on the set of all real numbers minus the set of real numbers where the denominator polynomial is 0. If f from x to y is a function, the set x is called the domain of the function, the set y is called the codomain, and the set of values of the function, that is the set of f x such that x is in x, which is a subset of y, is called the range of the function. As for example, if the total cost C of a firm per day as a function of the total daily output Q is given by C equal to C q, which is equal to 100 plus 8 q, where Q is in the set Q such that 0 is less than or equal to Q is less than or equal to 150. Then the domain of the cost function C is the set of Q such that Q is between 0 and 150, and the range of the cost function is Q such that Q is between 100 and 1300. Remarks. 1. Note that from the cost function that we have considered, cost value C can be found for any q, even for negative q. However, in the given situation, one has to specify the domain or should be well understood without any ambiguity. Then only one finds out the range. 2. In modern mathematics, one always specifies the codomain. We say that the function is onto if the range is the codomain. The phrase surjective function is also used for onto function, that is, f from x to y is onto if for each y in y there exists x in x such that f x equal to y. 3. When the values of the function are different for different values in the domain, we say that the given function is 1 to 1, 1 1 or 1 1 or injective. 4. In general notations, it means that f from x to y is 1 to 1 or injective if for all x 1 not equal to x 2 in x, we must have f x 1 not equal to f x 2. In other words, it means that if f x 1 equal to f x 2, then x 1 equal to x 2 for all x 1 x 2 in x. The last alternative phrase is very handy when one wants to prove that a given function is injective. 5. A function which is both injective as well as surjective is called a bijective function. In other words, a bijective function is both 1 1 and onto. Example. The example that we considered earlier, that is C equal to C q, which is equal to 100 plus 8 q, is injective as C q 1 equal to C q 2 implies 100 plus 8 q 1 is equal to 100 plus 8 q 2, which in turn implies q 1 is equal to q 2. Monotonic functions. If a function produces successively larger and larger values when we take successively larger and larger values from the domain, we say that the function is monotonically increasing or simply increasing, that is, a function is increasing if x 1 less to x 2 implies that f x 1 is less than f x 2. Similarly, if a function produces successively smaller and smaller values when we take successively larger and larger values from the domain, we say that the function is monotonically decreasing or simply decreasing, that is, a function is decreasing if x 1 less than x 2 implies that f x 1 is greater than f x 2. Inverse function. Suppose y equal to f x is a function, and if we write x equal to f inverse y if and only if y equal to f x, then clearly f inverse will be defined on the range of f, and moreover it will be 1 to 1 if and only if f is 1 1, and it will also be 1 many and therefore not a function if and only if f is many 1. So, if we want f inverse to be a function, f has to be 1 1 function. It will be defined on the range of f. Note that increasing or decreasing functions are 1 1 functions, and therefore, inverse from the range of the function exists. Here are some examples on inverse functions. Examples. 1. If y equal to f x is equal to 1 plus 3 x, then x is equal to f inverse y equal to y minus 1 divided by 3. 2. Note that y equal to f x equal to x squared does not have an inverse function as it is many 1 on R. 3. However, If we consider y equal to f x equal to x square for only non-negative x, then it is 1 to 1 and its inverse from the non-negative real numbers to non-negative real numbers exists and is given by x equal to f inverse y, which is equal to square root of y, the non-negative square root of y. Some of the very useful functions along with their graphs are displayed here. Linear function f from R to R defined by y equal to f x equal to a 0 plus a 1 x is called a linear function. Its graph for some chosen values of the constants a 0 and a 1 are displayed. Quadratic function f from R to R defined by y equal to f x equal to a 0 plus a 1 x plus a 2 x square is called a quadratic function. Its graph for some chosen values of the constants a 0, a 1 and a 2 are as shown. Cubic function f from R to R defined by y equal to f x equal to a 0 plus a 1 x plus a 2 x square plus a 3 x cube is called a cubic function. Its graph for some chosen values of the constants a 0, a 1, a 2 and a 3 are as shown. A rectangular hyperbola f from r minus 0 to r defined by y is equal to f x is equal to k upon x is called the rectangular hyperbola. Depending on k being positive or negative, we get the graphs as shown. Exponential and logarithmic functions f from R to R defined by f y equal to f x equal to a to the power x for a greater than 1 and in particular when a equal to e, we get what is known as exponential function. Some graphs for different values of x are shown in the figure. F from r plus to r defined by y equal to f x equal to log of x to the base a greater than 1 and in particular when a equal to e, it is called the natural logarithm and is denoted by y equal to f x is equal to ln x. Note that these functions, that is f x equal to a x and f x equal to log of x to the base a are inverse functions of each other. Let us have a look at their graphs. Summary: starting with the definition of order pairs and Cartesian product of sets, we have gone into the discussion of relations and functions. We also have introduced Cartesian coordinate plane. Discussion about graphs of relations and functions was carried out at a great length, showing how they can be plotted when they are given as subsets of the plane R square. Certain definite types of functions including increasing and decreasing functions and their graphs were also discussed. Inverse functions were also the part of the discussion. Thank you.